Okay, let's unpack this. Imagine looking up at the night sky, and there it is. A distinct reddish beacon winking back at us. For millennia, that red light Mars hasn't just been a celestial neighbor. It's been, well, kind of a mirror for our own aspirations, our fears, and our relentless curiosity. Our enduring fascination with Mars isn't just about what we see up there, but what it represented for our past and, crucially, what it promises for our future.
What's truly captivating here is how our understanding of Mars has transformed over the centuries. It's really evolved, from a mythical figure of war and destruction into this tangible world, a scientific puzzle, and now maybe a potential second home. So today, we're embarking on a, let's say, comprehensive deep dive through humanity's collective knowledge of Mars. We'll trace its story from its ancient mythological roots through the painstaking observations of early astronomers, all the way to the incredible cutting-edge science exploring its past and present, even peering into these really ambitious plans for human habitation. It's a journey supported by, well, an astonishing wealth of data.
And you, our listener, you've given us a fantastic stack of sources for this deep dive. Really everything from historical accounts tracing humanity's earliest observations to the detailed reports from the latest robotic missions and even these, visionary blueprints for future human settlements. We're going to meticulously extract the most important nuggets of knowledge and insight from all of this for you. So get ready for some serious aha moments, I think, some surprising facts, and maybe a fresh perspective on the red planet. So let's begin our journey not in space, but maybe in the realm of human imagination and belief, specifically ancient Rome. Imagine a burgeoning empire, right? Its very identity was forged in conflict and conquest, and at the heart of their fierce spirit was this fiery deity, a god of raw power and unyielding passion. That god was Mars, and his influence shaped not just their legions, but gave our celestial neighbor its very name. When we think of the Roman god Mars, we often conjure images of rage, of destructive passion, and the brutal realities of warfare. He embodied the raw, untamed aspects of conflict, a truly furious deity.
That's a powerful connection, yeah. It demonstrates how deeply rooted even our scientific understanding is in these ancient cultural beliefs. What's particularly striking about the Roman god Mars is how intimately intertwined he was with the very foundation and destiny of the Roman city-state itself. In early Roman civilization, Mars wasn't just a god among many. He was foundational, a central figure in what's known as the archaic triad. He ruled alongside Jupiter, the king of the gods, and Quirinus, who was actually the deified Romulus, one of Rome's legendary founders.
Wow, so right at the top.
Exactly. This places Mars at the absolute pinnacle of their early pantheon. It highlights his preeminent and essential role in the very identity and purpose of the budding Roman state. He was seen as, a divine protector and a source of martial strength.
And his mythological importance runs deep, quite literally, into the origin story of Rome itself. Mars was famously the father of the twin brothers, Romulus and Remus, the legendary founders of Rome. And this wasn't some distant, abstract thing. It was a tale of lusty Mars fathering them with Rhea Silvia, a Vestal virgin. It lends this powerful, almost primal energy to the city's origins. This direct lineage from a powerful war god underscored how his divine fury was perceived not merely as destructive chaos, but as a driving, almost sacred force. It was believed to inspire and empower Roman military achievements, fueling their conquests and their eventual dominance. His rage in this context was a catalyst,
A
right?
catalyst for civilization and conquest, yeah.
Yeah.
A force that propelled Rome forward, precisely.
Okay.
However, as Rome matured and transformed from this regional city-state into a sprawling empire,
Right.
and as it began to embrace the intellectualism and, let's say, sophisticated cultural values of the Greeks, Mars's preeminent position in the Roman pantheon underwent a gradual but significant shift. He eventually lost some of his top-tier status to Minerva, the goddess of tactical and strategic warfare.
Ah, interesting. So strategy over brute force.
Exactly. This reflects a broader cultural evolution within Rome itself, a move from an emphasis on sheer brute force and raw, untamed fury, to a more refined appreciation for calculated strategy, cunning, and intellectual prowess in battle. It was a societal shift, from pure aggression to organized, thoughtful conquest.
And it's not just the planet itself that carries these mythological echoes. The planet Mars has two small, irregularly shaped moons, both named after figures directly connected to the Greek war god Ares, who is Mars's Greek counterpart.
Right, Phobos and Deimos?
Phobos meaning fear, and Deimos meaning flight. They weren't just arbitrary names, were they?
No, not at all. They're named after the mythological horses that pulled Ares' chariots into battle, so they act as this constant celestial reminder of the planet's aggressive, combative namesake.
It's pretty poetic, really, how these tiny celestial bodies orbiting the red planet forever whisper tales of ancient gods and epic conflicts. Okay, so we've explored the foundational myths that shaped our very perception of Mars. But how did that perception begin to transition from lore to actual understanding? From myth, let's fast forward several centuries to the advent of the telescope,
Right.
which literally opened the floodgates for our scientific understanding of Mars. Suddenly, the red planet was transformed from a mere twinkling point of light into a discernible world with its own distinct features.
Yeah, the very first known drawing of Mars, based on telescopic observation, dates back to 1636. It was by Francisco Fontana of Naples, at a time when telescopes were still, pretty crude and astronomers were just beginning to map the cosmos. Fontana made a simple yet profound observation. He famously noted that the planet's disk appeared not uniform in color.
Which sounds minor now, but back then.
It was a huge leap. It hinted that Mars wasn't a perfect featureless sphere, but a complex body with variations across its surface. It really set the stage for more detailed mapping later on.
And it was observations like these by a brilliant Dutch astronomer named Christian Huygens in 1659 that truly began to transform Mars from a mythical beacon into a tangible, rotating world. He observed a large, dark, V-shaped feature on Mars's surface, which we now know as Syrtis Major Planum.
Yeah.
This dark patch was prominent enough for him to track its movement over several nights. What was it about his method that allowed him to achieve such incredible precision with the rudimentary tools of his time?
Huygens' genius lay in his meticulous, persistent observation and his logical deduction. Really careful work. By carefully plotting the changing position of Syrtis Major, he could infer that Mars rotated on its axis. And his calculations were astonishingly accurate. He concluded that Mars rotated in about 24 hours.
That's incredibly close.
It is. His refined estimate, published later, of 24 hours and 40 minutes for a Martian day was remarkably close to the modern value of 24 hours and 37 minutes. That level of precision, achieved with telescopes that were essentially long tubes with lenses, was a monumental achievement. It laid the groundwork for future planetary studies. It confirmed Mars was a dynamic world, not just a distant star.
Building on that, in 1666, the French-Italian astronomer Giandomenico Cassini, another giant of early astronomy, made a fascinating observation: bright white patches at Mars's poles. He noted these distinct features, but it was Giacomo Maraldi in 1719 who made the crucial follow-up discovery that unlocked their true nature.
What did Maraldi find?
Maraldi observed that these polar caps weren't static, they actually grew and shrank with the changing Martian seasons.
Oh, okay. Seasonal changes.
Exactly. These early observations, made possible by increasingly powerful telescopes, laid critical groundwork for understanding Mars as a truly Earth-like planet in some ways.
But it was a great British astronomer, William Herschel, who, in 1781, made a deduction that was truly monumental. It fundamentally shifted our understanding. He correctly deduced that these white areas were indeed polar ice caps, similar to those on Earth.
Ice caps, just like ours.
Yes, and his meticulous work didn't stop there. By observing the movement of these polar caps and other surface features with incredible patience and precision, Herschel was able to calculate Mars's axial tilt, estimating it to be approximately 24 to 28 degrees relative to its orbit.
And Earth's is.
Earth's axial tilt is very similar at 23.5 degrees.
Wow.
This was a profound realization because it meant Mars must experience seasons just like our own planet, a powerful indicator of shared planetary mechanics.
Okay, here's where it truly gets interesting and connects to our daily lives. Because Mars has an axial tilt so similar to Earth, it experiences the familiar cycle of spring, summer, autumn, and winter.
Right, the same basic pattern.
However, due to Mars's longer orbital period around the Sun, a Martian year lasts 687 Earth days. Each Martian season would be nearly twice as long as ours.
Nearly double. Imagine that.
So imagine a summer that stretches on for 6 months, or a winter that lasts for half an Earth year. This discovery truly brought Mars closer to home, showing us a celestial neighbor that shares a fundamental, relatable characteristic with Earth, yet on a vastly different timescale.
And it definitely sparked a wave of speculation about life on Mars, didn't it? Understanding its seasonal cycles was a big part of that early fascination.
So we've peered through those early telescopes, gaining glimpses of a rotating seasonal world. But nothing truly prepares you for seeing a planet up close.
Nothing compares to being there, even robotically.
Exactly. That's precisely what changed everything when humanity finally sent its robotic ambassadors to Mars. This era of robotic exploration dramatically transformed our perspective, giving us our first real close-ups. This all began with pioneering flybys and orbiters. The very first successful mission to Mars was NASA's Mariner 4, which executed a flyby on July 15, 1965, our initial fleeting handshake with the red planet.
Yeah. And the impact of Mariner 4 was immense and, for many, quite sobering. In its brief encounter, it transmitted a mere 22 black and white images back to Earth. Only 22.
Which doesn't sound like much now.
No. But before this, popular culture and even some scientific theories had painted this picture of Mars as potentially habitable, maybe even home to a dying civilization building intricate canals. Percival Lowell's famous maps.
Oh yeah, the canals. That was huge for a while.
It captivated the public imagination for decades. But the pictures from Mariner 4 were frankly a shock. They revealed a surface that wasn't covered in romanticized canals or imagined vegetation. Instead, it was barren, desolate, and heavily cratered. It looked far more like our own moon than Earth.
So, kind of a letdown for the alien civilization crowd.
A big one. This single flyby effectively shattered the prevalent paradigm of a civilized Mars. It replaced it with a much more somber understanding. Mars appeared to be geologically dead, stark, and unwelcoming. A profound reality check. It forced scientists to completely reevaluate their assumptions.
And then, a decade later, in 1976, we saw a pivotal moment with the Viking 1 and 2 landers. These weren't just flybys. They touched down on the Martian surface with a suite of sophisticated experiments designed specifically to search for signs of life.
A much bigger step.
Among them was the controversial labeled RELEASE, or LR, experiment. This experiment actually yielded positive, repeatable results consistent with extant microbial life. That sounds huge. Seemingly proving life existed there. It must have sent shockwaves through the scientific community.
It absolutely did. But this is where it gets incredibly complex and, frankly, remains this kind of haunting anomaly in Mars exploration. Despite those strong, repeatable, positive results from both Viking landers, which were thousands of miles apart, mind you, the conclusion remained, and still largely remains, highly controversial.
Why controversial if the results were positive and repeatable?
Well, the main reason was that the positive results, this burst of radioactive gas release after adding nutrient solution to the soil, were entirely obliterated when the soil samples were heated to 160 degrees C. And furthermore, long-term storage of samples at around 10 degrees C completely destroyed whatever was causing the reaction.
So heat and cold killed it. That sounds biological.
It strongly suggests a biological agent that's temperature sensitive, yes.
Yeah.
Few purely chemical agents that could oxidize the LR nutrients are affected by such relatively low temperatures. That heat and cold sensitivity is a compelling argument for biology. However, a significant portion of the scientific community ultimately concluded the responses were non-biological. They attributed it to some as yet unidentified oxidant in the Martian soil.
An oxidant?
Yeah, something very reactive chemically. The argument was that if there were robust life forms, other Viking instruments, like the gas chromatograph mass spectrometer, GCMS, which looked for organic molecules, should have found clear evidence. And they didn't.
Okay. Conflicting results.
Exactly.
Yeah.
Yet the LR experiment's unique temperature sensitivities have never been fully explained by non-biological means. It's still debated. And what's crucial to remember is that these LR data represent the only data we will ever have on biologically pristine Martian samples, given the potential for later contamination by terrestrial microbes carried on subsequent missions.
So those samples were unique.
Absolutely unique. It underscores the immense challenge of proving extraterrestrial life when our only frame of reference is Earth-based biology, and the critical importance of returning samples to Earth for definitive answers. The debate still simmers,
A true scientific mystery that continues to challenge our assumptions. Okay, then came the Mars Global Surveyor, or MGS orbiter, which operated from 1997 to 2006. This mission gave us a much longer-term view of Mars, observing it for 4 Martian years.
4 whole Martian years, yeah.
It revealed consistent weather patterns driven by solar energy, and its data was so good that scientists could even accurately predict dust storms, like those during the landing of the European Beagle 2 lander. That's a significant step in understanding Mars as a dynamic system.
Definitely. The MGS's Thermal Emissions Spectrometer, or TES, provided absolutely critical atmospheric data. It built a comprehensive picture of Martian climate variability. For instance, it showed that global atmospheric temperatures during the 1997 perihelion, when Mars is closest to the Sun, were significantly colder by 10 to 20 Kelvin compared to Viking data from 1977.
Colder even when closer to the Sun.
Yes, which points to complex atmospheric dynamics. The TES data also indicated that the global aphelion atmosphere, when Mars is farthest from the Sun, is colder, less dusty, and cloudier than previously established by Viking climatology, even after Viking data revisions. A later comparison, while acknowledging the microwave record as most representative, noted no measurable trend in global average temperature between Viking and MGS overall. But it did find this strong dichotomy between the northern and southern hemispheres.
A dichotomy. How so?
The northern spring and summer are relatively cool, less dusty, and richer in water vapor and ice clouds. Meanwhile, the southern summer is warmer, dustier, and has less water and ice. This strong hemispheric difference tells us a great deal about the circulation of the Martian atmosphere and how solar energy is distributed and trapped. These continuous, consistent weather patterns observed by MGS offered invaluable long-term climate insights. We're still building on that data.
And other orbiters, like the 2001 Mars Odyssey and the Mars Reconnaissance Orbiter's Mars Climate Sounder, have continued to contribute vital atmospheric data, right? Building on this foundational understanding of Mars's climate, adding layers of detail to our climate models. So if orbiters gave us the global atmospheric view, then the rovers have allowed us to truly unpack Mars's past and present, getting up close and personal with the Martian surface. So what does this all mean for our understanding of Mars's history? The Mars exploration rovers, Spirit and Opportunity, landing in 2004, they completely reshaped our understanding of Mars's watery past.
Oh, absolutely. Game changers.
They delivered incontrovertible evidence that liquid water once flowed on Mars.
Absolutely. Opportunity, landing in Meridiani Planum, found scientific gold almost immediately. It discovered small, spherical concretions of the mineral hematite, affectionately nicknamed blueberries, because of their shape and color.
Right, the blueberries. I remember those pictures.
And layered sedimentary rocks rich in the mineral jarosite. On Earth, both of these minerals typically form in the presence of standing, acidic water. This was the first direct, in situ smoking gun proof of a past, watery environment on Mars. It wasn't just speculation anymore. We had physical evidence right there.
So acidic water initially?
Initially, yes. But later, in its incredibly long mission at the rim of Endeavour crater, Opportunity found gypsum and clay minerals. These form in more neutral pH water. And that was even more exciting, because neutral pH water is a far more hospitable environment for life than acidic water.
More suitable for life as we know it.
Exactly. Opportunity also has the distinction of discovering the first meteorite ever found on another planet, an iron-nickel rock that provided further clues about the solar system's formation.
And Spirit, landing in Gusev Crater, also made incredible discoveries, though its initial findings were a bit of a curveball, right?
They were. Initially, the crater floor was covered in volcanic basalt. Interesting, but it seemed to hide any ancient lake sediments they hoped to find.
But Spirit kept going.
It did. Spirit's perseverance paid off. After traversing the plains and bravely ascending the Columbia Hills, it found rocks clearly altered by aqueous fluids, including those rich in carbonates and the mineral goethite, telltale signs of past water interaction.
Okay, so water evidence there too.
Yes, but Spirit's most stunning discovery, and perhaps one of the most exciting aha moments of the whole MHER mission, came by accident.
An accident? How?
After one of its wheels failed and got stuck, the team had to ingeniously drive the rover backward, dragging the dead wheel.
Oh, I remember that.
This action churned up a patch of bright white soil that was found to be 90% pure silica.
Pure silica, what does that mean?
On Earth, such deposits form in hot springs or volcanic fumaroles environments known to be teeming hotspots for microbial life due to both liquid water and a chemical energy source. This suggested Mars not only had surface water in its past, but also hydrothermal systems, a truly tantalizing prospect for the possibility of ancient Martian life.
Wow. Both rovers, though, being solar-powered, they faced serious threats from those massive dust storms in 2007, didn't they?
They did. Existential threats. These storms were so immense and opaque that they severely reduced the energy from their solar panels, sometimes by as much as 99%.
99%? How did they survive?
It necessitated shutting down most science experiments. It nearly caused the permanent failure of both rovers. Mission controllers had to execute extreme power-saving measures, just hoping the storms would clear. It really underscored just how harsh and dynamic the Martian climate can be and the incredible engineering resilience required to operate there.
Spirit didn't make it through another one later, though.
No, Spirit eventually succumbed to a dust storm in 2010. But Opportunity, incredibly, continued for over 14 years before finally going silent in 2018 after another planet-encircling dust storm, a testament to its design and its team.
building on their incredible legacy, Curiosity, which landed in 2012, has continued to uncover Martian history with unprecedented detail. Its mission is focused on whether Mars ever had the right conditions to support microbial life, right?
Correct. It's been exploring Gale Crater, an ancient lake bed, for over a decade now.
And just recently, I saw this news, July 24, 2025, its ChemCam instrument captured this captivating image of a coral-like rock formation.
Yes, that was fascinating. This intriguing structure, less than an inch long, formed by mineral-rich water seeping into cracks in the rock billions of years ago. As the surrounding rock eroded away due to wind, this harder, mineralized structure was left behind, a silent testament to Mars's watery past.
It's a vivid, tangible reminder of how much the planet has changed and how ancient water carved its way through the landscape. Really cool looking.
And then we had Perseverance, which landed in February 2021. This represents the absolute cutting edge of robotic Mars exploration. It's the most ambitious rover yet, explicitly tasked with searching for biosignatures, direct signs of past microbial life.
So looking directly for life signs, not just habitability.
Exactly. And it's also the first leg of a crucial, multi-mission Mars sample return campaign. It's meticulously collecting and caching pristine rock and soil samples from Jezero Crater for a future mission to retrieve and bring back to Earth.
Why Jezero Crater specifically?
It was specifically chosen because of compelling orbital evidence of an ancient lake and a beautifully preserved river delta. That's considered an ideal environment for preserving any signs of past life that might exist. These samples, once returned, will allow Earth-based labs to perform analyses far more sophisticated than anything a rover can do on Mars.
And alongside Perseverance, we had Ingenuity, the little helicopter that could.
Haha, yes, Ingenuity. What a fantastic success story.
It proved powered flight was possible on another world. How many flights did it make? 72 successful flights. A groundbreaking demonstration of aerial mobility on Mars. It soared over Perseverance, scouting routes, providing unique perspectives, really paving the way for future aerial exploration. It opened up new dimensions for understanding planetary surfaces. Each of these robotic explorers, from the pioneering Mariner 4 to the sophisticated Perseverance and Ingenuity, has added crucial, indelible pieces to this incredible evolving puzzle that is Mars. Okay. Moving from past discoveries to present realities, let's talk about the red planet today. Its climate, the conditions we'd face there. In short, it's harsh, unforgiving, and dynamic. The average temperature on Mars is a frigid -63°C or -81°F.
Bone-chillingly cold on average.
But that's just an average, and averages can be deceptive, can't they? There are extreme temperature differences. For example, at the equator during summer, the surface at noon might reach a relatively balmy 20°C or 68°F.
Almost comfortable for a moment.
But then plummets to -73°C at night, sometimes within mere hours. And at the poles during winter, temperatures can drop as low as -153°C. Colder than anything natural on Earth.
And the reason for these dramatic and rapid temperature swings is Mars's exceptionally thin atmosphere. It's mostly carbon dioxide, but its pressure is only about 1% of Earth's at sea level. Just 1%.
So barely an atmosphere at all compared to ours.
Pretty much. This thin atmosphere has very low thermal inertia. It simply cannot retain solar heat effectively. Think of it like a very thin, tattered blanket on a freezing night. As soon as the sun goes down, all the warmth rapidly radiates away into space. There's almost no atmospheric mass to trap and redistribute heat. Hence, those wild daily temperature variations.
And we can't forget those notorious dust storms. We saw their devastating impact on Spirit and Opportunity.
Nearly mission enders.
Nearly ending their missions in 2007 and eventually leading to Opportunity's demise. Scientists have found that these regional dust storms are closely related to the availability of dust on the surface, meaning certain areas are more prone to them.
And these can grow into planet-wide events, can't they?
Exactly. They can drastically alter surface conditions, visibility, and even global temperatures by blocking sunlight. They are a formidable force of nature on Mars.
What's also compelling is the undeniable evidence for ongoing climate change on Mars itself, a natural planetary process separate from Earth's anthropogenic warming. The Mars Global Surveyor observed these Swiss cheese features in the South Polar ice cap, specifically Plenum Austral.
Swiss cheese features, what are those?
They're distinctive pits and patterns in the frozen carbon dioxide layer. And these pits were seen to grow larger by about 3 meters per Martian year due to the sublimation of dry ice.
Sublimation, that's solid turning straight to gas, right?
Correct. Solid CO2 turning directly into gas, bypassing the liquid phase.
And NASA explicitly stated that this suggests climate change is in progress on Mars, a natural, long-term shift. At the current rate of loss, these dry ice deposits at the South Pole might be entirely gone in just 100 years or so.
It's a stark reminder that other planets have dynamic changing climates driven by their own complex physical processes.
This rapid sublimation on Mars, contrasted with Earth's climate change, really highlights how planetary climates can shift dramatically even without biological drivers, doesn't it?
It does. It forces us to consider the universal principles of atmospheric physics and energy balance, and how delicate that balance truly is, regardless of the planet. It's a powerful natural experiment unfolding before our eyes, offering insights into climate dynamics that extend beyond Earth. But despite these intriguing observations of a dynamic atmosphere, it's important to note that we still lack in situ measurements on things like dust electric charges or atmospheric electric fields on Mars.
Why are those important?
They're crucial for understanding how dust storms initiate and grow, and how they interact with the upper atmosphere. Vital information for planning human missions. The European Space Agency's Schiaparelli EDM lander, part of the ExoMars mission in 2016, was designed to collect such data during its descent and on the surface.
Oh, I remember that one. It didn't end well.
No, unfortunately it failed during its automated landing. Crashed due to a software glitch.
Ah, shit.
So this highlights a significant gap in our understanding of certain atmospheric dynamics. Vital data we still need. However, on a more positive note, we do know that Mars's soil and atmosphere contain several vital elements crucial to life as we know it.
Like what?
Sulfur, nitrogen, hydrogen, oxygen, phosphorus, and carbon. The basic building blocks are there, providing a foundation for future possibilities, should life ever emerge or perhaps be introduced.
Okay, given all this knowledge we've gained about Mars, the ultimate human endeavor now is charting a direct course to the Red Planet. This isn't just about a single mission, it's about establishing a sustained human presence beyond Earth.
A huge leap.
NASA, for its part, has laid out a comprehensive and integrated roadmap for deep space exploration called the Moon to Mars, or M2M architecture. And this strategy heavily leverages international and commercial partnerships, aiming for a truly global, collaborative effort.
Yeah, NASA frames this ambitious undertaking with three core pillars, answering the fundamental question of why we should explore beyond Earth. First, there's science. The relentless pursuit of new scientific knowledge about the universe and our place in it. Pretty straightforward. Second, national posture. This focuses on establishing and maintaining national strength and technology, innovation, and competitiveness on the global stage, driving economic growth, creating high-tech jobs. And third, inspiration, aiming to inspire an all-new generation in STEM fields, science, technology, engineering, and mathematics, igniting their curiosity and encouraging them to pursue careers that will shape the future.
So science, tech leadership, inspiring the kids.
Essentially, yes. These pillars collectively advance human leadership, foster economic development, and ultimately aim to improve the human condition through exploration and discovery.
And the approach to Mars is meticulously gradual and risk-averse, isn't it? Building capabilities step by step, not a single leap, but a methodical climb.
Very methodical.
It starts with human lunar return, reestablishing a human presence on and around the moon with missions like Artemis. Then comes foundation exploration, which involves longer stays on the lunar surface, learning to live and work for extended periods in deep space.
Practicing near home first.
Exactly. Followed by a sustained lunar evolution, working closely with international and commercial partners to create a bustling lunar economy and infrastructure. Only after leveraging all that experience, proving technologies, and building operational capabilities in the lunar environment, will NASA aim for the first human missions to Mars. It's a phased, strategic approach designed to maximize success and minimize risk.
And for those initial human missions to Mars, the objectives are quite specific and ambitious. A crew of 4 will travel to Mars orbit, with 2 members descending to and living on the surface for a 30-sol stay.
30 sols. That's about 31 Earth days, right?
Roughly, yes. A critical aspect to this initial approach is the pre-deployment of cargo. Multiple uncrewed landers will go ahead, years in advance, preparing for the crew landing by pre-placing essential supplies, equipment, maybe some initial scientific instruments.
Sending the luggage ahead makes sense.
Exactly. There will be minimal initial surface infrastructure, meaning no permanent habitat will be set up before the crew arrives. This reflects a lean, all-up mission approach where the crew departs Earth with all of the transit propellant needed for the round trip, rather than relying on in-situ fuel production for the very first return. It's about proving the capability for a relatively short, impactful surface stay before building a permanent presence.
And a major player in this Moon to Mars vision, especially for enabling a sustained human presence on the red planet, is SpaceX with its Starship vehicle. It's truly a powerhouse, designed to be fully reusable and capable of carrying unprecedented amounts of mass to orbit and beyond.
Indeed. SpaceX's strategy envisions uncrewed starships leading the way. These initial missions will deliver an unprecedented amount of cargo, around 100 metric tons per mission to the Martian surface.
100 metric tons per trip. That's huge.
That's enormous. To put that in perspective, that's roughly equivalent to the mass of about 25 large African elephants, or the payload capacity of 5 space shuttle orbiters combined per trip. This precursor work is absolutely critical. It's for pre-placement of supplies like habitats, rovers, life support systems, developing initial infrastructure like power generation and communication relays, testing key technologies in the harsh Martian environment, and crucially, conducting detailed resource prospecting, especially to map and characterize water ice for future in-situ resource utilization, or ISRU.
ISRU, using local resources.
Exactly. This isn't just delivering cargo, it's setting the entire stage for human arrival.
And this highlights the methodical nature of the plan. Human Starship flights are optimally planned to occur after these initial uncrewed missions have done their work. This ensures that essential resources and infrastructure are already pre-staged on the surface, significantly enhancing the safety and success probability for the arriving human crews.
It's about laying the groundwork properly, building a robust logistical chain before putting human lives at risk. Smart planning. Beyond just delivery, Starship is also designed with the game-changing capability to return crew and cargo from Mars back to Earth.
A round-trip ticket.
A reusable round-trip ticket. This is achieved by refilling propellants on Mars itself, utilizing local resources processed through a surface propellant production plant. This ability to refuel on Mars fundamentally alters the economics and feasibility of sustained missions. It reduces the need to launch all-return propellant from Earth.
Huge cost saving, I imagine.
Massive. Furthermore, the human starships will have a very large pressurized volume, around 1,100 cubic meters.
How big is that in real terms?
To put that in perspective, that's roughly equivalent to the entire habitable volume of the International Space Station, or the interior space of maybe 6 average-sized houses. This immense volume, most of which will be dedicated to human habitation during transit, transforms the months-long journey from being cramped in a tiny capsule to having genuine living and working space.
That seems vital for a long trip.
Absolutely vital for crew morale, psychological well-being, and long-term physical health during transit.
Okay, all these incredible vehicles and ambitious plans bring us face to face with perhaps the most formidable challenge of all. Us, humans. Our bodies simply aren't built for the immense distances and harsh conditions of interplanetary travel, are they? The flesh is weak, as they say.
Well, it certainly wasn't evolved for deep space.
The profound impact of interplanetary travel on the human body and mind presents major hurdles for human missions to Mars. This is where it gets truly fascinating, because it forces us to confront our biological limitations in extreme environments.
You're absolutely right. The human element is paramount, and it introduces a whole new layer of complexity. Let's break down these critical physiological and psychological challenges. First, distance and communication delay. A round-trip journey to Mars takes many months, stretching sometimes over 2 or even 3 years, depending on the orbits.
Years away from Earth.
Exactly. And the sheer distance results in a significant one-way communication delay, ranging from 4 to 24 minutes.
4 to 24 minutes one way.
One way. This rules out any possibility of real-time interactions with Earth. Imagine trying to have a conversation where each response takes up to half an hour to receive, or a crucial command taking that long to reach the surface in an emergency.
So, no quick calls to Houston for help?
None. This necessitates an incredibly high degree of autonomy for Mars settlers. They won't be able to rely on immediate guidance or support from mission control. If a critical system fails or a medical emergency arises, the crew must be trained and equipped to handle it entirely on their own, often without immediate expert consultation from Earth. They truly will be on their own for significant periods. It requires a profound shift in operational philosophy. Second, radiation exposure. This is arguably the most pressing physical threat to human health in deep space.
A big one.
The big one. Astronauts will face 2 main types of radiation: galactic cosmic rays, or GCRs, and solar particle events, or SPEs. GCRs are high-energy protons, helium nuclei, heavy nuclei originating from outside our solar system, essentially a constant shower of atomic bullets.
He's nasty.
They're particularly dangerous because they're extremely difficult to shield against. Ordinary physical shielding often fails, and in fact, insufficient dense shielding can actually increase the radiation dose.
Wait, shielding can make it worse? How?
Imagine trying to block a cannonball with a thin sheet of paper it just rips through. But if you use something slightly thicker, say a thin steel plate, it might fragment the cannonball into 1,000 tiny, still dangerous shards. That's sort of what happens with high-energy GCR particles and suboptimal shielding. They collide with the shield and create a shower of secondary, lower energy, but still harmful radiation particles.
Okay, so the shielding itself has to be carefully designed.
Incredibly precise.
Yeah.
Material choice and density are vital. SPEs, on the other hand, are mostly protons, but highly energetic ones, ejected from the sun during solar flares or coronal mass ejections. They're less frequent, but can deliver an extremely high dose in a short period.
So how much radiation are we talking about overall?
Well, to quantify the risk, a round-trip Mars mission could expose astronauts to a minimum of 0.66 sieverts of radiation.
How does that compare to, say, an ISS astronaut?
It's more than 3 times the career limit for NASA IS astronauts, and is roughly equivalent to receiving about 632 head CT scans.
Wow, that's a lot.
It is. While not immediately lethal, this exposure significantly increases the lifetime risk of various cancers, neurological damage, cardiovascular disease, and other long-term health issues. So, to mitigate this severe threat, several strategies are being developed and tested. For shielding, the most effective materials are those rich in light atoms, especially hydrogen. They're most efficient at disrupting high-energy particles.
Like water.
Exactly. Water, polyethylene, a common plastic, even novel materials like hydrogen-rich boron nitride nanotubes are being investigated. An elegant solution is to design spacecraft so that the crew's water supply, wastewater, even food are stored within the habitat walls. Dual purpose, life support, and radiation protection.
Clever. What about those solar particle events?
For SPEs, crews can retreat to small, heavily shielded storm shelters within the spacecraft or habitat to wait them out. They typically last hours to days. Once on Mars, habitat design will likely involve building underground or covering surface habitats with several meters of Martian regolith, the local soil, to provide natural, effective shielding.
Using Mars itself as a shield.
Precisely. More advanced long-term concepts include generating a protective active magnetic field around the spacecraft, like Earth's magnetosphere, to deflect charged particles. There's also research into pharmaceutical countermeasures, drugs that could help the body repair or protect cells from radiation-induced DNA damage, boosting the body's natural defenses. Third challenge, microgravity and reduced gravity effects. Mars's surface gravity is only 38% of Earth's.
38%, not zero, but much less.
Right. And the long-term health effects of this reduced gravity environment for sustained periods are largely unknown. But we have extensive data from astronauts living in microgravity on the ISS that gives us crucial clues.
What kind of clues?
One major concern is bone density loss. The lower mechanical load on bones leads to a rapid decrease in bone mineral density, potential osteopenia or osteoporosis, making bones brittle and prone to fracture.
How do they fight that?
Countermeasures include daily, intense weight-bearing exercise using specialized equipment, pharmacological interventions, and a diet rich in calcium and vitamin D. There's also significant immune system dysregulation. Astronauts experience decreased immune cell counts, increased inflammation, reduced ability to fight infections. Oxidative stress can also increase.
So getting sick is a bigger risk.
Potentially, yes. Cardiovascular deconditioning is another issue. Altered heart rate, blood pressure regulation, changes in blood volume, and vessel stiffness can lead to fainting upon return to higher gravity. And concerningly, there are neurological impacts. Subtle brain structural changes, shifts in cerebrospinal fluid, potential cognitive performance decline.
Wow, it affects everything.
Pretty much. Other physical issues include decompression sickness during EVAs or spacewalks due to the pressure difference between the suit and the habitat. NASA has rigorous protocols for that.
Like the camp out.
Exactly, the camp-out protocol. Astronauts can also experience altered cutaneous sensations, changes in touch and temperature perception, and even potential hearing loss from constant machinery noise. Finally, and equally critical, is the immense psychological strain.
Being cooped up for years, millions of miles from home.
Exactly. Crew members will be confined to a small space, a literal tin can, for years, isolated from humanity, with communication delays precluding real-time emotional support, and unable to return home quickly in an emergency. The monotony, isolation, confinement, It will be immense, potentially leading to depression, anxiety, interpersonal conflict, cognitive impairment.
How do you even prepare for that?
Current strategies from ISS missions and terrestrial analog habitats like HICs are extensively studied and applied. Things like mandatory journaling for an emotional outlet and research data. Social activities are crucial. Shared meals, celebrating milestones, playing board games with Velcro pieces so they don't float away.
Velcro board games.
Communication with family, though delayed, is vital. Astronauts on ISS make delayed calls, read bedtime stories. Entertainment is critical. Music, films, books, VR for immersive games or nature experiences to combat sensory deprivation, virtual exercise sessions. And critically, professional support through regular check-ins with psychologists and flight surgeons, offering mental health support from Earth despite the delays. These are complex, multifaceted challenges requiring holistic solutions. The human spirit is resilient, but it definitely has limits.
That's an incredible list of challenges to contend with. But it leads us right into the fascinating prospect of what life might actually be like for the first Martians. How do we even begin to simulate such a demanding existence? We can draw significant insights from the ISS, of course, but also from those terrestrial analog missions like the Hawaii Space Exploration Analog and Simulation, or HIC's habitat on Mauna Loa.
Right, the analog missions are key.
They provide a critical glimpse into the daily routines and challenges of long-duration space habitation right here on Earth.
Yet, a high-sea simulation provides a very grounded, practical picture of what a Mars habitat might feel like. Participants live in a 13,000 cubic foot white dome. Not spacious for a long duration, roughly a small 3-bedroom house, shared by a crew of 6, with equipment taking up much space.
Cramped quarters.
Definitely. Every time they venture outside, whether for geological surveys or maintenance, they must don cumbersome spacesuits, reinforcing the simulated alien environment and the constant barrier. And those 20-minute communication delays each way with the outside world are a constant, palpable reminder of their isolation. It leads to profound feelings of loneliness. One participant described it as emotionally crippling at times, highlighting the immense psychological toll.
Wow.
Inside, there's a simulated airlock, composting toilets, no flushing water, and showers are typically limited to just 8 minutes per person per week to conserve precious water.
8 minutes a week.
Per week. Food largely consists of shelf-stable ingredients. Tortillas, rehydrated vegetables, peanut butter. Fresh food is a rare, highly anticipated treat, maybe grown in a small on-site greenhouse. The setup mirrors the roughing-it conditions expected on Mars, forcing extreme resourcefulness and high autonomy, preparing crews for situations where Earth can't provide immediate guidance.
So with communication delays leading to profound loneliness and the need for incredibly high autonomy, it really forces us to ask, will future life on Mars be this bleak outpost staffed by a few dozen people like Matt Damon in The Martian?
Right.
Or can it evolve into a thriving, perhaps even independent colony? That transition from mere survival to true living is the ultimate goal, isn't it?
It is indeed the ultimate goal, and to even establish a basic existence, let alone thrive, fundamental life support systems are absolutely crucial. They must be closed loop as much as possible to minimize resupply from Earth.
Closed loop meaning recycling everything.
Everything possible. Actively recycling every drop of water from urine, condensed moisture in the air from breathing and sweating, even extracting it from the soil. This recovered water can then be broken down via electrolysis to produce fresh oxygen for breathing. Additionally, specialized scrubbers use chemical reactions or physical adsorption to actively remove toxic carbon dioxide from the air.
How much water and oxygen does a person need per day?
To give you an idea, each person breathes the equivalent of about 0.9 kilograms of liquid oxygen and requires roughly 2.7 kilograms of water per day. Minimizing resupply from Earth means these systems must be highly efficient, robust, and reliable for years on end. That's a significant engineering challenge.
This brings us to perhaps the grandest, most long-term vision for Mars. Terraforming. It sounds like something straight out of science fiction, doesn't it? Reshaping an entire planet. So what does this all mean? Can we truly make Mars a second Earth? A place where humans could one day walk outside without a spacesuit, breathe the air, feel the rain? It's a concept being actively discussed, however challenging it may be.
Well, the core idea of terraforming is to significantly change Mars's climate and atmospheric composition to make it more habitable for humans, ultimately making it capable of supporting complex Earth-like ecosystems. One of the more, let's say, controversial ideas popularized by Elon Musk involves detonating nuclear weapons on the ice caps to release large amounts of water vapor and CO2, theoretically warming the planet and thickening its atmosphere.
Nuking Mars. Does that actually work?
Well, recent, more rigorous research by NASA scientists disputes its effectiveness. They suggest that even if all the CO2 currently trapped in Mars's poles and soil were released, it would only increase the atmospheric pressure to about 7% of Earth's.
Only 7%. That's still incredibly thin.
Far too thin for human breathing or sustaining liquid water on the surface for long. It wouldn't be sufficient to achieve the desired atmospheric changes for full terraforming based on current estimates of available CO2.
Okay, so if nukes aren't the answer due to insufficient available CO2, what other methods are on the table? And how feasible are they?
One proposed method is the introduction of super greenhouse gases. This would involve manufacturing and releasing massive quantities of potent artificial greenhouse gases, like perfluorocarbons, PFCs, or sulfur hexafluoride, SF6,
Gas is much stronger than CO2.
thousands of times more effective at trapping heat. A sustained industrial-scale release could theoretically initiate the warming needed to sublimate the existing polar caps and release what little CO2 is available in the regolith. Another concept involves orbital mirrors, or soletas, enormous lightweight mirrors, perhaps tens to hundreds of kilometers in diameter, placed in orbit around Mars to reflect additional sunlight onto the surface, specifically focusing it onto the polar ice caps.
Like giant space magnifying glasses?
Kinda, yeah. The concentrated energy would increase temperature and accelerate the release of frozen gases. Then there's albedo reduction, darkening the surface. Darker surfaces absorb more sunlight, leading to warming. Proposals include spreading dark dust from Mars's moons, Phobos and Deimos, or introducing hardy, dark-colored extremophile organisms like lichens and algae that could survive and slowly spread.
Painting Mars darker, essentially.
Letting life paint it darker. And a very recent 2024 study proposed a fascinating new approach using conductive nanorods made from Martian minerals like aluminum or iron. These nanorods, dispersed in the atmosphere, would scatter and absorb thermal infrared radiation, warming the planet. Potentially 5,000 times more effective per molecule than fluorine compounds. Still very theoretical, of course. But even with significant CO2 release and warming, there's the monumental challenge of atmospheric pressure. As we noted, Mars's atmosphere is incredibly thin. To reach an optimum pressure for humans to survive without pressure suits around 100 kilopascals or 15 psi, Earth's sea level pressure additional volatiles would be needed beyond just CO2.
More gas needed than Mars currently has locked up.
Likely, yes. This could mean redirecting several massive asteroids, maybe totaling 40 to 400 billion tons containing ammonia, a source of nitrogen or other volatiles, to bombard Mars and contribute to the atmosphere.
Redirecting asteroids, that sounds difficult.
It's a staggering undertaking. Manipulating celestial bodies on an unimaginable scale. Definitely science fiction territory for now.
What's encouraging, though, and provides a glimmer of hope for these ambitious ideas, is that Mars once had an atmosphere maybe as thick as Earth's and abundant liquid water. We see the evidence in its ancient riverbeds and lake deltas.
True, the past environment was very different.
And its soil also contains many of the main elements crucial for life. Sulfur, nitrogen, hydrogen, oxygen, phosphorus, carbon. This provides a natural foundation, doesn't it? A hint that these terraforming ideas aren't entirely starting from scratch. They're attempts to restore Mars to a more Earth-like state, leveraging its inherent potential.
And NASA is already funding research into ecopoiesis, which is the creation of an ecosystem on a lifeless planet. Baby steps towards terraforming. This involves developing sealed biodomes containing oxygen-producing cyanobacteria and algae designed to grow in Martian soil, using subsurface ice as a water source.
Little self-contained ecosystems.
Exactly. The idea is to send small canisters with these extremophile organisms, maybe corkscrew them into selected sites, and monitor for oxygen production, demonstrating the very first steps towards a breathable atmosphere. There's also ongoing research into the potential of genetic engineering for crops. For instance, a 2023 study showed that genetically modified rice could be made more perchlorate resistant to grow in Martian soil simulants mixed with potassium perchlorate.
Perchlorates, those are toxic, right?
Yes, a common Martian contaminant. The modified rice grew, even if at a reduced rate.
Yeah.
This is about making Martian agriculture viable in the long run.
Okay, so to truly make life on Mars independent and self-sustaining, rather than a constant drain on Earth's resources, a critical element will be in situ resource utilization, or ISRU. This raises an important question. How do we leverage what's already on Mars to reduce our reliance on Earth-supplied materials, moving from an outpost to a truly self-sufficient future?
ISRU is absolutely foundational for a sustainable Mars presence. The most valuable resource on Mars for ISRU is its vast deposits of water ice, found in the polar caps and beneath the surface in various regions. This water is critical not just for life support drinking water, oxygen for breathing, future agriculture, but also for producing rocket fuel,
Fuel from water.
hydrogen and oxygen via electrolysis. Consider this. Each kilogram of consumable material transported from Earth to Mars incurs a massive penalty of about 200 kilograms of propellant just to launch, transfer, and land it. ISRU of water ice effectively eliminates this huge launch mass penalty for return journeys and surface operations. It makes a self-sustaining civilization feasible and dramatically reduces mission costs and complexity. For water extraction and processing, several methods are being designed. One promising concept is ride well systems, like the Redwater project, using coiled tubing and compressed Martian air to melt and extract water from depths up to 25 meters,
Drilling for water, basically.
sort of melting its way down. Other alternatives include open-pit strip mining, where machinery removes the dry overburden to expose ice layers, or even controlled explosives to fracture and expose subsurface ice. Once extracted, the raw water would need rigorous chemical purification to ensure it's potable and free of contaminants like those perchlorates. For construction, autonomous excavation, drilling, and building using local Martian materials will be key to rapidly expanding infrastructure, creating berms for radiation protection, roads for mobility, landing pads for safer arrivals. An innovative proposal involves using sulfur, which is surprisingly abundant on Mars, as a binding agent for Martian concrete.
Concrete made with sulfur.
Yeah. Preliminary Earth-based trials show this sulfur concrete has comparable compressive strength to terrestrial concrete and offers excellent resistance to Martian challenges like radiation and extreme temperature swings. And critically, to protect against constant cosmic radiation, future Martian cities will likely be built underground, leveraging the regolith as natural, cost-free shielding. Subterranean habitats are inherently safer and more stable. Energy production on Mars will rely on a combination of solar power with advancements in dust mitigation technologies to keep panels efficient and nuclear power.
Nuclear seems essential for reliability.
Absolutely. Nuclear power, particularly small modular reactors, is crucial for reliable, continuous energy, especially during long dust storms or Martian nights when solar energy is insufficient. It ensures habitats remain powered and life support runs uninterrupted. Transportation and communication systems are also vital. Development of robust, modular manned vehicles for exploration and transport across the vast Martian surface, using autonomous navigation powered by AI. For communication back to Earth, strategic use of Mars's L2 Lagrange point of gravitationally stable position beyond Mars is proposed for communication satellites.
A relay station in space.
Exactly. These could potentially use solar sails for station keeping, requiring minimal propellant, and operate autonomously with AI for continuous data relay, creating a high-bandwidth link back to Earth. And finally, agriculture. Essential for food supply and air revitalization, moving beyond freeze-dried rations. Aeroponics growing plants without soil in nutrient-rich mist is promising, avoiding potential contaminants in Martian regolith. Algae bioreactors are also being explored. Algae are incredibly efficient at converting light and CO2 into biomass, offering solutions for air revitalization, waste recycling, and a protein-rich food source.
So farming algae.
Potentially a big part of it. And research continues on genetically modified crops, like that perchlorate-resistant rice, pushing the boundaries of what can be grown in an extraterrestrial environment. Putting all these pieces together, a proposed timeline for human presence on Mars envisions the first crewed missions in the mid-2030s. These would involve short-term stays focused on research, initial habitat setup, and exploiting ISRU resources like water ice. By the late 2030s to early 2040s, we could see the establishment of a permanently inhabited base with significant expansion of ISRU, large-scale water extraction, oxygen production, beginnings of controlled environment agriculture.
A real foothold.
Yes. And finally, by the 2040s, the audacious goal is to develop a self-sustaining colony pushing towards true independence from Earth, a fully operational Martian society. It's ambitious. That's the trajectory.
What an incredible, sprawling journey we've taken today. From the furious Roman god Mars and the mythological narratives that shaped our earliest perceptions, to the painstaking telescopic observations that first revealed it as a world, through the cutting-edge science and engineering of robotic exploration, and finally, to these ambitious, intricate blueprints for human colonization. It's clear that while the road ahead is long and filled with immense challenges from cosmic radiation to psychological isolation, the progress made and the sheer ambition driving us forward are truly extraordinary.
Yeah, and we connect this to the bigger picture. Mars colonization really transcends simply establishing a human presence on another world, doesn't it? It represents this monumental journey to broaden our cosmic understanding, to push the boundaries of technology, and to catalyze growth in various fields right here on Earth. From advanced material science to personalized medicine, robotics, AI, it ignites imaginations worldwide, inspiring a new generation to look beyond the immediate and consider the grand possibilities. What new, unforeseen challenges will we discover as we get ever closer to making the Red Planet our second home? And perhaps even more profoundly, what will those challenges teach us about ourselves, about our limits, and maybe our boundless capacity for innovation and survival in the universe?
A truly fascinating thought to ponder as we wrap up this deep dive into Mars. Thank you for joining us.